provides two important services to a computer system. It provides abstraction and arbitration. Abstraction means hiding the details of different hardware configurations so that each application doesn't have to be tailored for each possible device that might be present on the system. Arbitration means that the operating system manages access to shared hardware resources so that multiple applications can run on the same hardware at the same time without interfering with one another. Now, these hardware resources that need to be managed include the CPU, the hierarchy of memory, all the input-output devices on the system, and to some degree, the power and system management features of the system. Many of these features are handled directly by the hardware, but the operating system is involved, particularly in energy conservation. Now, the abstraction features of the operating system allow hardware devices manufactured by different manufacturers to have the same interface within software for applications to use. These hardware devices all have different low-level instruction sets. They all have particular capabilities, features, and details that are unique to each hardware device. If we didn't have a common interface into these hardware devices, first of all, our variety of hardware might be limited, but worse, every application on the system would have to be programmed to use every single device on the system. An example, back in the 1990s, computer games often required internal programming for specific video cards and specific sound cards. It was often necessary to go into the settings for each game and tell the game what type of video card you had, what type of sound card you had, for the purpose of configuring the game to use that particular hardware. Imagine if that had to be done for every single application on the system, including, say, a calculator or a web browser. That would be a very untenable situation in terms of being able to make use of computers the way we use them today. Also, what if we could only run one program at a time on a computer system? Years and years ago, that was the case. However, a modern system is running multiple applications simultaneously, and it's up to the operating system to ensure that all these applications can access resources. So each CPU is divided among the different programs. Each program gets access to memory, input-output, as well as disk. And in an ideal world, the operating system also enforces policies that isolate applications from each other, so that a crash in one application doesn't take down the entire system or other applications. Now, of these examples, do we have a situation where we have abstraction or arbitration? Well, first example is supporting both Intel and AMD processors. This is an example of abstraction. We don't have to write separate software for an Intel processor relative to an AMD processor, at least for 99.99% of applications. Simply write the application once, it will run on either processor. Switching between applications is an example of arbitrating hardware resources among the different applications on the system. Separating memory allocated to different applications is also an arbitration activity. It keeps one application from overwriting the contents of memory that's being used by another application. Enabling video conferencing software to use different camera devices. This would be an example of abstraction. The video conferencing program just has to know how to use a camera interface that the operating system provides, and then different cameras from different manufacturers can be used without having to write the application, the video conferencing program, to be able to talk to each individual camera. Similarly, accessing two different hard disks from two different manufacturers. Any underlying detail differences between those drives can be handled by using the operating system to extract away the details. Sending and receiving messages over a network is both abstraction and arbitration. On the one hand, we're abstracting away the details of each particular network card to be able to send and receive the message. On the other hand, we're sharing that network card among all the different applications on the system. Now, we can think of the system in terms of layers. At the bottom of the layer cake, we have the hardware. This is what executes the software, top three layers. The operating system is the middleman, so to speak, between the applications and the libraries and utilities upon which the applications depend, and the underlying hardware. Specifically, the core of the operating system, or the kernel, so named after, say, a kernel of corn, is the minimum piece of software that's needed to share the hardware between the different applications. Whatever lives outside the kernel that is software is said to be in user space. That means it's application code, or sometimes even parts of the operating system, that are not strictly necessary to share the hardware or abstract away its details. Now, operating systems implement a common mechanism for allowing applications to access the hardware, which is abstraction. And the applications make requests from the operating system to go and access the hardware or other features by making system calls down into the operating system. This is called entering the operating system, or entering the kernel from the top half. Operating systems are also able to alert applications that hardware has changed. Perhaps a network packet has come in. Perhaps the user has pressed a key on the keyboard. These alerts are delivered via a system called interrupts and refer to entering the kernel from the bottom half, from the hardware side of the operating system. We should also note that operating systems can manage and terminate applications by sending signals to those applications. Now, there are a wide variety of operating systems out there. They basically fall into two categories: Microsoft Windows, which is not Unix, and everything else, which is Unix. Microsoft Windows systems, non-Unix systems, are the most popular desktop operating systems at the moment. However, they're rapidly being eclipsed by tablet devices, most of which are running Unix-style systems. Windows is typically pre-installed by PC manufacturers, which accounts for a good portion of its present popularity. Unix systems, on the other hand, are installed by the end user, except for commercial Unix systems and Mac OS X. Mac OS X is probably the best-selling Unix system of date. And Linux, which includes the Android platform, is probably second. Now, there are some mainframe systems out there also, some of which are Unix-like. Some use custom operating systems. There are a variety of players in the embedded systems market. However, that's presently dominated by Android, with Apple's iOS, which is based on Mac OS X, in close second. Others, Symbian, BlackBerry OS, TinyOS, are confined to smaller markets. Now, the idea behind the Unix systems began with a time-sharing system started in 1964 called Multics. And the idea behind Multics was to make computing into a remote service that could be accessed by terminals using telephone lines. It wasn't terribly successful because dial-up connections at the time, at about 9600 baud, were rather slow. However, Canada actually did have a Multics system deployed and used it as part of their national defense network until the year 2000. Multics is remembered, however, primarily for its influence as a multi-user shared system. And today, with cloud computing, there's some significant parallels between some of the cloud computing models that we use and some of the ideas that were pioneered back in the Multics system. Now, Unix was actually a play on the term Multics. It was developed by Bell Labs in 1969. It's actually a trademark term, so some authors use Starnix to refer to the family of systems, and used the word Unix only for the commercial distributions. The original Unix systems were commercial distributions, with free variants BSD and Linux coming along late 80s and early 90s. Now, Unix systems are time-sharing systems in that they support multiple users at the same time, but they're designed to be run on local computer resources instead of remote resources. The Berkeley system distribution, which was based on AT&T's commercial distribution, was one of the first open source Unix systems to emerge. It was based on the commercial distribution, so AT&T sued UC Berkeley, but an eventual settlement allowed Berkeley to distribute BSD freely in both source and binary form. Today's descendants of BSD include FreeBSD, OpenBSD, and Mac OS X, which is based on the Unix BSD system. Linux, however, was an alternate approach to getting a Unix-like kernel running on a computer system. This was started by Linus Torvalds as an undergrad at the University of Helsinki, released in source code form in 1991, and often combined with a set of user space, utilities, and libraries created by the GNU project. Thus, the resulting combination is sometimes called GNU/Linux. It has been commercially successful for many device classes, including web servers, network and embedded devices, and mobile phones. Some people, including myself, use Linux as a desktop platform, and it does have the benefit of having one kernel that's scalable from embedded devices all the way up to supercomputers. Now, what is Linux? Well, generically, the term Linux refers to a class of operating systems that use a common kernel. Now, distributions of Linux, or operating environments as they're sometimes called, are cobbled together by taking the Linux kernel and adding various different user space tools to it. Many of these core tools originated in the GNU project, which originally started at MIT, and thus systems are sometimes called GNU/Linux instead of just Linux. I typically, however, say just Linux, referring to either the kernel itself or to the operating system distributions that are based upon that kernel. The Linux kernel was originally started as a hobby by an undergraduate at the University of Helsinki, a gentleman by the name of Linus Torvalds. He still heads the kernel development project. Now, Linux is what's called a monolithic kernel, and that means that the device drivers are built into the kernel. However, it's not a true monolithic kernel because the device drivers can be built as modules and loaded and unloaded from the kernel at runtime. The latest stable version was 2.6.37 on January 5th of 2011. That has since been updated to version 3.03, I believe, was the latest version that I've seen as of now, which is late August 2011. The latest version can also be checked by going to www.kernel.org. Here is an example of some of the main components of Linux operating system. At the lowest layer, we have the computer hardware. And on top of that hardware, we have the Linux kernel. The Linux kernel contains a number of built-in subsystems that enable access to the computer hardware. These include drivers, memory management, process management, file systems, networking, including sockets and protocols, and other utilities that the kernel provides. On top of the kernel, we have the GNU C library, upon which most other libraries are based, since C is typically the lowest level system language to which all other software is eventually compiled. On top of that, we have our compiler, GCC, some important utilities called core utils, also part of the GNU project, and the born-again shell, or bash, which provides a command line interface into the system. All we need in order to run a Linux system and do useful things with it is everything below this line where I'm moving the mouse right here. All the software above this line is add-on software that's not strictly needed in order to run a Linux system, but makes Linux systems more convenient or do other things. So for example, we can add network tools such as Secure Shell Server and a generic services server called inetd that can launch all kinds of different services. We can also run a LAMP stack that stands for Linux, Apache, MySQL, PHP. If we're in a desktop scenario, we can also run a graphic user interface. This includes X11, specifically the X.org distribution, and one of a number of different environments that can be run inside X11. Popular ones include GNOME, KDE, and XFCE, which isn't on this particular graphic. Now, a large number of people have come up with different distributions of Linux. These distributions contain different sets of software, but they all share the Linux kernel in common. We typically classify distributions by which package manager they use. Unlike Windows and Mac systems, where we install individual applications and then have to manually update each application by running separate installers, Linux distributions typically use package managers, which download and install extra software and update existing software with a single command. These package managers include the Red Hat Package Manager, or RPM, which is used in Red Hat Enterprise Linux, Fedora, Mandriva, OpenSUSE, and a number of other distributions. A competing package format is the Advanced Package Tool. This is used primarily by Debian and derivatives of Debian, such as Ubuntu. There are other binary formats, however, in use. Slackware uses a TGZ format with its own package management commands. Arch Linux has a custom-written package manager called Pacman, and there are some others out there. There are also source formats. Gen 2 is able to build everything from source using ebuilds. Linux from scratch isn't so much a distribution as it is a book that tells you how to put together your own Linux system by compiling sources for each particular application. This is, of course, time-consuming. And there are other source formats out there as well. Now, in industry, Red Hat Enterprise Linux is quite popular. It's a Linux distribution from Red Hat Incorporated, which is based in Research Triangle Park, North Carolina. That's in the Durham area. It is an open-source distribution, but the official product is sold with an update subscription accessed via per installation serial numbers. Therefore, in order to get the update subscription and the installation media, it's necessary to purchase the subscription from Red Hat. They do use the RPM package format. In fact, they invented it. RPM stands for Red Hat Package Format. CentOS is a free rebuild of Red Hat Enterprise Linux that's widely used in academia and industry on many high-performance computing systems and for many other applications. This, of course, uses the RPM package format and is available at zero cost. Fedora Core is a community distribution that's sponsored by Red Hat that grew out of an old product that Red Hat used to produce, which was called Red Hat Linux without the enterprise part. And Fedora is used to develop and test packages and infrastructure that are later incorporated into the enterprise Linux product. Debian is a fully open source distribution which avoids proprietary software and has an emphasis on security and stability. The stable version of Debian is extremely stable because the packages are extremely well tested. The flip side is that those packages tend to be rather dated, and thus an unstable version is available if more bleeding-edge packages are needed. Debian uses something called the Advanced Package Tool, or APT, in order to manage its software. Ubuntu is actually based on Debian. It's sponsored by a company called Canonical Limited, which is based in South Africa. It's designed to be easy to use and friendly to new users switching from competing platforms. There's a new release every 6 months, and it's often necessary to completely reinstall the operating system at each new release. There is a functionality that's built into the advanced packaging tool called disk upgrade, which seems like a great idea on paper, but in practice often doesn't work right and leaves the system unstable. Ubuntu also has a package pinning policy. Thus, once a package is released, it's only updated for security updates. If new features are added, one has to wait till the next version of Ubuntu comes out before getting the newly updated package. Now, Arch Linux, which is what I personally run, is a minimalist framework for creating a custom system. It's not so much as a distribution as it is a set of tools that enables each individual to create his or her own installation, customized to his or her own desires. It's a different philosophy from traditional distributions. It is a completely written from scratch distribution. It's not based on any other, and it is what's called a rolling distribution. There are not discrete versions of Arch Linux. Every time you run a system update on Arch Linux, you get the latest version of the operating system, along with the latest version of all application packages, and all the latest bugs. And the Pac-Man Package Manager, which was written from scratch for Arch Linux, is used to manage the software. So these are just a few examples of different Linux systems, different Linux distributions that can be used with the highly scalable Linux kernel. In particular, I'll talk about disk attachment, talk about some of the properties of magnetic disks, discuss disk addressing, discuss partitioning, and introduce solid-state drives. I'll begin with disk attachment. Disks are attached to the motherboard via some kind of cable, and the exact type of cable depends upon the bus in use on the system. There are several different types of bus, which are implemented by different chips attached to the motherboard on the different computer systems. One common bus that was widely in use until the early 2000s on consumer-grade hardware was the Integrated Drive Electronics, or IDE bus. This has been since backronymed Parallel ATA, or PATA. It consisted of 40 to 80 ribbon cable connecting to a 40-pin connector to provide 40 simultaneous parallel channels of communication between the motherboard and the hard drive. Enterprise-level systems of that time period typically used SCSI, or Small Computer System Interface buses, which consisted of the cabling of 50 to 80 pin connectors between the hard disk and the motherboard. SCSI also defined a standard set of commands, a standard protocol, for interfacing with disks, CDs, and other types of storage devices. This protocol was useful for recordable CD media and DVD-ROM media, and was implemented on the ATA bus using the SCSI protocol in a system known as a TAPI, or ATA Packet Interface. Now, in modern times, serial interfaces between the motherboard and the disk have replaced, for the most part, the parallel interfaces. For ATA-style disks, we have serial ATA, or SATA, which replaces the 40-pin connector with a 7-pin connector. It still uses the same protocol, either ATA or a TAPI protocol. And serial-attached SCSI, or SAS, which uses the SCSI protocol over a narrower channel consisting of 26 to 32 pins. Both of these new serial attachment mechanisms support higher bus transfer speeds, enabling theoretically faster devices to be attached to the motherboard. It does not necessarily mean, however, that the disks have gotten that much faster. Now, we still store large amounts of information using magnetic disks. These are metallic or glass platters that are coated in a magnetic surface, and a stack of these platters is rotated at high speed by an electric motor. A stack of heads moves back and forth across the platters, altering the magnetic fields in order to read and write data. Moving the heads back and forth results in seek time, and waiting for the platter to rotate around to the correct position results in rotational delay. Historically, magnetic media were addressed by geometry. The smallest addressable unit of space on a hard disk is called a sector. This is typically 512 bytes, at least on older disks, though other sizes have been used, and newer drives go up to 4 kilobytes. Tracks are circular paths at a constant radius from the center of the disk, and each track is divided into sectors. One head reads from a single track on a single side of each platter. When you stack multiple heads up, using multiple tracks on the various sides of several different platters, the result is what's called a cylinder. And historically, accessing disks required accessing the particular data locations using cylinder head sector or CHS geometry addressing. As disks grew larger and faster, however, this type of addressing scheme became limited, and so logical block addressing was put into use, and it's now the standard today. Logical block addressing, or LBA, gives each block on a disk its own logical address, and leaves it up to the disk firmware to convert the logical addresses into physical locations on the disk. Current standards with logical block addressing on ATA will allow enough space for disks up to 128 heavybytes. Operating systems normally implement these 48-bit addresses using 64-bit data structures. Thus, operating systems that support 64-bit disk addressing can generally support hard disks up to 8 zettabytes of data, assuming we're using 512-byte sector sizes. Now, regardless of the size of the disk, it is convenient to partition the disk into multiple sections so that we can isolate data from each other. We can isolate the main partition of the operating system from a partition we would use for swapping out pages of virtual memory, for example, and we can isolate that from user data. Also, with early hard drives, it was convenient to isolate partitions so as to minimize seek time by making it such that the head didn't have to move as far in order to access data. Now, there are two types of partition table, or data structure that resides on the disk to indicate where on the disk the different partitions lie. A common partition table type that's in widespread use today is the master boot record-based partitioning scheme. And the way this works is that the BIOS on the system, the basic input-output system, actually loads the first 512-byte sector from the boot drive at boot time, and code stored in that 512-byte sector loads the rest of the system. Also within that sector is stored the partition table, which is called the DOS-style partition table. And the DOS partition table still uses legacy cylinder head sector addressing, supports a maximum of 4 primary partitions, one of which can be an extended partition with logical drives in it, and supports maximum partition sizes and maximum partition starting addresses at 2 tebibytes. This is the default partitioning scheme for Microsoft Windows and most Linux distributions. However, as hard drives become larger and grow past 2 terabytes, the GUID partition table, or GPT, starts to be used. This is the larger partition table that can support disks or partitions up to 8 zettabytes in size. For compatibility with old partitioning tools, or to prevent old tools from overwriting sections of the disk and seeing a discrete space, a protective or dummy master boot record is retained at the beginning of the disk. GPT is the default partitioning scheme in Mac OS X, is an optional partitioning scheme in Linux, and is supported in 64-bit versions of Windows 7, Windows Vista, and Windows Server 2008, provided that the system uses the extensible firmware interface, or EFI, instead of the legacy BIOS interface. For Linux, the Grub2 bootloader can use a legacy BIOS interface, but it requires a dedicated small partition on the hard drive in which to store the rest of the bootloader. Now, hard drives and magnetic media are used for large quantities of space because of their relative low cost. When high performance is required, we prefer to use solid-state drives, or SSDs. These drives have no moving parts, which makes them generally faster and less subject to physical damage than mechanical hard disks. Most of these SSDs use NAND flash memory to store data, and this is a storage mechanism that's based on injecting or removing an electron from a flash cell. Injecting an electron into a flash cell changes its state from 1 to 0. So this is backwards from what one would expect. An empty flash cell actually has a state of 1 instead of 0. The membranes through which this electron is injected and removed eventually wear out, typically after anywhere from 100,000 to 1 million cycles. Furthermore, the electrons tend to leak out over long time periods of many years, causing flash to lose data, which makes flash-based memory systems unsuitable for long-term backups. In this diagram, we can see how a solid-state drive using flash memory works. Blank flash memory stores the value 11111111. So we have all ones here. If I want to write the value 10010100, I have to pop electrons into the 2nd, 3rd, 5th, 7th, and 8th flash locations, the 8 bit locations. I'm pretending we only have a byte here. If later I wish to change that stored value to 10100011, I must first erase that block of flash memory before I can program the new data value. Generally, I must erase flash memory in the size of an erased block, and this is typically 4 kilobytes. Waiting for this block erasure procedure causes something called write amplification, where successive writes to an SSD become progressively slower. To avoid this problem, typically erase the SSD ahead of time whenever space has been freed on it. And there's an ATA command called trim that facilitates this process. One other issue that has to be dealt with SSDs is the fact that each cell can only be written to and read from, or generally written to, erased and written to, a fixed number of times. This is typically between 100,000 and 1 million. So to spread out the writes across the entire SSD, the SSD moves data around the drive as files are updated, and it also reserves a certain amount of free space unused so that that free space can be swapped in and out with space that's in use later. This process, called wear leveling, has the advantage of dramatically increasing the useful life of the SSD and reducing write amplification whenever clean blocks are made available. However, in order for the write amplification reduction to be effective, the operating system and the underlying file system must support the ATA trim command. And furthermore, it's impossible to ensure that the disk is secure against forensic data recovery because it may not be possible to overwrite and properly erase the reserved cells of memory that have been taken out of service. Thus, a used solid-state drive should be physically destroyed instead of attempting to resell it, which can be an issue because a solid-state drive has a higher upfront cost. So in summary, disks are attached to the system via some kind of bus. The newer bus styles are SATA and SAS. These modern disks are addressed using logical block addressing. They're partitioned either with DOS partition tables or GUID partition tables. GPT use will increase as the size of disks becomes larger owing to the limits of the DOS partition table. And solid-state drives offer higher performance at a higher initial cost, subject to the requirement of wear leveling, and subject to not being able to be safely resold due to the inability to forensically secure the data on the drive.